introduction by the next plenary talk. So I'm very happy to introduce to you to Thorvaldur Thordarson, who was one of my PhD supervisors, actually. And he's, at the moment, he's Professor of Volcanology and Petrology at the Faculty of Earth Sciences at the University of Iceland. He has specialized in hotspot volcanism, in particular in Iceland, but also in Hawaii, the Northwest US, and other areas worldwide. His research is on physical volcanology, eruption history, volcanic stratigraphy, shallow conduit processes, and the timescales of magmatic processes. He's especially interested in the modes of emplacement of lava flows and their impacts on the environment and the climate. So thank you very much for being here today and to talk about the recent eruptions in Iceland. Thank you.
Thank you, Mari, for a very nice introduction, and thank you for inviting me here. It's been a very exciting time. First time in Mexico, so that's a new thing. I see the session that this is attached to deals a bit with earthquakes and precursors of volcanic eruptions. Well, since I'm a physical volcanologist, not a seismologist or a geodetist, I'm going to skip very quickly through the precursors and get into the real eruption. And try to describe these two events that took place in Iceland in 21 and 22. And they took place on the peninsula which we call Reykjanes Peninsula in southwest Iceland, where also majority of Icelanders live. It's the most densely populated region in Iceland. Not very densely populated, but still has about 250,000 people. And that sort of put these eruptions a bit, well, let's say it put the people a little bit into context of what volcanic eruption can potentially do when it comes to have an impact on infrastructure and also on communities. And hazard management is also one point that is a very interesting topic, and I've been involved in that quite a lot. But if I started talking about hazard management associated with these events, it would be a very complicated story, because it not only deals with impact on population, but also on very complex infrastructure, but also relates to tourism. Because these are very tourist-friendly eruptions. And on the first day, we had 5,000 people at the eruption site. So anyway, I'm going to focus on the physical volcanology of these eruptions. And a brief outline. I'm going to start with telling you where and what Iceland is. Very briefly talk about the geology and the volcanism on the Reykjanes Peninsula. Skim through these precursors as fast as I can, and then get into these two eruptions that took place in March to September 21 and August 22. Can I try to finish off with saying something about erupted magmas and the origin of them, and some sort of concluding remarks. Okay. So where is Iceland? It's in the North Atlantic, middle of the North Atlantic. It is a fairly big highland plateau or mountain plateau that rises more than 3,000 meters above surrounding seafloor. It has an area of about 200,000 square kilometers and a volume of about 8 million cubic kilometers. It makes it one of the biggest igneous provinces8 million cubic kilometers of magma. It actually sits on the mid-ocean ridge. This is the Reykjanes ridge that comes up to shore of Iceland and actually connects to the Reykjanes Peninsula. And then, as you can see here, the plate boundary, the mid-ocean ridge kind of zigzags across Iceland and continues as Kolbeinsey Ridge into the Arctic. Reason why Iceland is as big as it is and why it rises so high is because right underneath Iceland is a mantle plume. Some people call it the headless cat because of its shape. And the center of it is roughly here in central Iceland, south central Iceland. And so the buoyancy from that and added magma volume is the reason why Iceland exists, is above sea level. It's the only part of the mid-Atlantic ridge which is above sea level. A little bit about Reykjanes. Reykjanes Peninsula. This is quite a barren area. It features the Reykjanes volcanic belt, and the igneous rocks are very porous. So even though it rains a lot, whenever you go to Reykjanes, it's raining. There's no really running surface water on here. So it's actually quite dry from the point of view of plant life. But anyway, Reykjavik capital is here, Keflavik Airport is over here, and there are a few other communities around. And it features the, like I said, the Reykjanes volcanic belt, which is basically a volcanism that takes place on the plate, along the plate boundary across the Reykjanes Peninsula, which is highly oblique to the spreading direction. So in here we have extensional faults, but it's dominated by actually strike-slip faults. And we have some magmatism, as I mentioned earlier. So this is probably best described as a leaky transform rather than an oblique rift. And this is just showing the plate boundary as geodetic surveys suggest it may lie in Iceland. And post-glacial volcanism in the Reykjanes Peninsula in the last 40,000 years is basically a map showing the distribution of those volcanic units. And the oldest units are pickrite, Pahoehoe lava shield, very small ones. They're dotted sort of many along the south coast here, covered less than 10 square kilometers and a volume of less than 0.5 cubic kilometers. The most voluminous formations are the olivine tholiites, which have magnesium content between 6 and 10 weight percent. The picrites extend way up, further up. And these are shown here in green. Those are all the lava shields. The main construction unit of the Reykjanes Peninsula during the Holocene. And they cover about 700 square kilometers. Individual go up to 167. The total volume is 32 cubic kilometers. And biggest lava shields, so this one here called Hayden Howe. It's about 10 cubic kilometers. And we have a series of Holocene fissure eruptions as well, which are largely superimposed on the lava shield, or intercalated with the lava shields. And there's 100 of them in total. They cover roughly about 600 square kilometers, but are only 1/3 of the total volume of the lava shield. Very similar petrologically and geochemically to the lava shield product, even though they're slightly more evolved. So to finish off the volcanism on the background volcanism on Reykjanes Peninsula, when we map out and date individual eruptive units, what we found, at least in the, haven't gone further back than 4,000 years, is that eruptions take place in very distinctive periods. These periods are about 200 to 400 years long, and in each of these periods, the whole peninsula activates. So you have eruptions along systems across the whole peninsula. And typically these eruptions, in one place, they will occur as what we call fires, which means that we have a series of eruptions on a single volcanic lineament over periods of 10 to 30 years, and we group those eruptions into fires. And then each of these lava flow fields represent separate fires. The periods in between, which range from 600 to 1,000 years in length, average about 800. There's no volcanic eruption. We have seismicity, but no volcanic eruptions at all. And nota bene, Before 21, the last eruption on the Reykjanes Peninsula was 1240, which in 21 was 781 years earlier than when the Fagradalsfjall eruption happened. So basically, we're right on schedule with next eruptive episode, which we think is actually starting now with the Fagradalsfjall fires. And these two eruptions are the first two events of that sequence. See how that goes? Yep. Now, a little bit about the run-up to these eruptions. And what we see here is the seismicity. All earthquakes of magnitude greater than 1 in the year 2000, late 2019, I think it's from December 2019 and through 2020. And you see there's a buildup of seismicity during this period of time. What we also have are these two locations here, which are locations of inflation and deflation that were detected first in January 2020 and until June 2020, and then later over here in an area called Krýsuvík in August 2020. These sites are on either side of the future eruption site. And those people who have worked on these things and studied those things, listed papers here, they don't agree on how to interpret this. Some of them say this is magmatic intrusions which are related to this buildup of magmatic activity, intrusive activity into the crustal zone on Reykjanes. But Florence et al., they suggest that these were actually primarily CO2-rich critical or supercritical fluids with a little bit of magma. And both have arguments for and against. I'm not going to make a judgment on that. You just have to read the papers. And but in February, late February 21, there was a significant jump in the seismic activity, and we started to get events that were in the magnitude 5 to 6 range. And they were quite felt strongly in the Reykjavik area and scared a lot of people. And same time, we detected uplift and also a fairly large horizontal displacement, shown here by the red line. And nota bene, on 19th of March, we had an eruption. Take also note, just quickly, that seismicity drops significantly right after the eruption starts. It ended on 18th of September. Seismicity picks up again. We get significant pulses in October, November, and December 21, also in May 22. And then we get another very sharp sort of a seismic swarm in late July 22, which led to the second eruption on 3rd of August. So that's sort of summarizes really up the seismic aspects of things and geodetic aspects of things. But this is from the paper of Sigmundsson et al., where they're actually really looking in detail on the 24th and the 19th of March time frame. And the open black circles are all the earthquakes of magnitude 1 and greater in that time period. See, they're quite concentrated on Fagradalsfjall, but also spread along the plate boundary. All of the starred one are greater than 5 magnitude earthquakes, and they are all strike slip. They actually have along north-south trending fault planes. Also shown here is the horizontal displacement on stations, geodetic stations, west of the Fagradalsfjall complex, where the eruption site ended up being. And also on the east side, we can see a more eastward or east-southeastward kind of displacement. All fits quite nicely with what they modeled is this was a dike injection, a regional dike. They claim it's 9 kilometers long and in 2 segments. And the eruption took place above the southern segment of that dike. And just as an interest, we can see also that about half of the earthquakes in this time period was related to the dike injection, 25% to movement on the plate boundary, another 25% to other unexplained sources. Okay, I need a video. Someone needs to click on. Anyway, so it's there, fine, great. So, as you can see, this is actually video taken a few hours after the eruption started. And it started on a 180-meter long lineament with 10 to 12 vents, active vents, which were just basically oozing out magma, feeding very small, narrow channels, and this is a discharge of approximately 4 cubic meters per second. This is the start of the eruption. Most eruptions start with a big bang and a good show. This one barely made it to the surface. But it kept going, and it kept going for 6 months. And you can see this is just the vent. It's just bubble bursting, continuous bubble bursting events that typified the activity for the first week. But the eruption started at 8:30 in the evening on 19th of March. Now, hopefully I can stop this and skip. Yep. So, we had an eruption. As typical Icelanders, the minute they hear about an eruption, they get in their car and they drive as far as they can, and the rest, they walk or run, and they go directly to the vent. And this lava channel here, which is now, by this time, activity had actually concentrated on 2 vents, which are called 1A and 1B, and this lava channel is feeding actually sort of a slabby and rubbly Pahoe flows. It's just starting to fill up this valley, Geldingadalir, which is the name that the eruption takes its name after. And hopefully, video again. Brilliant. I was just going to show you this. This is actually a time lapse of the activity over 15 days for this phase of the eruption, the beginning of the eruption. And we can see quite nicely very continuous sort of bubble bursting events at the vents. A lot of interesting things happening there, feeding these narrow channels of lava, pooling here, then bifurcating again. And also, look, a notice of these darker masses that are moving. These are actually stiffer, slightly older lava, but is still moving, even though it does not have any incandescent. So it's actually really good education in terms of how lava moves, but we don't have time to watch it all. For the first 13 days, the magma composition stayed reasonably constant. We were erupting magma with potassium titanium ratio about right around 8 to 8%, just slightly over 8 to 8%. And only because we were there almost every day, and we were sampling in situ every other day, which meant we had the sample set resolution to actually detect this change that took place after day 13. Certainly that ratio of these incompatible elements started to rise. And over the next 25 days or so, it kept rising. Then it leveled out by day 39, and we were primarily erupting this magma here, which has here potassium titanium ratio, same magnesium content. We would have, if we have not gone out and sampled it right away, we would have never gotten this. Number one, because this is not accessible anymore. Most of it is actually under later lava. Anyway, so this is barely sort of mildly enriched magma. This is actually quite enriched magma and quite volatile rich. But this chemical change is actually also very significant because it cause change in all other eruptive parameters. For example, here is vent 1A and B. On 5th of April, we had two vents open up 600 and 800 meters north of vent 1A. That was followed by another vent opening up here on 7th of April, another one opening up here on 10th of April, and then two new vents on 13th of April, vent 5 and vent 6, and vent 5 is important, keep that in mind. All of these vents, except vent 5, became inactive by end of April. All the activity was after that concentrated on that single vent. Parallel to this, we have a jump in magma discharge. This is dense rock equivalent, 3.7 to 8.2 cubic meters per second, double the gas release. Oops, this probably goes back, right? Yes. Changed the activity at the vent. This very low intensity bubble bursting event is feeding lava out, changed to actually episodic fountaining with on a minute interval. Later on in June, that interval became hours, and then in July and August, it was days. And this is actually quite nicely reflected in the tremor data. So the tremor really follows and records the pulsating activity, which is driven by magma degassing in the shallow conduit and bubble generation. And so it basically records all these events quite nicely, helps with timing of things and sorting things out. Can you have two videos now? Please? Yeah. It will come here. Yes. Yeah, click on it. Good. Okay, so what we have here is 4th of May and 9th of August. This is just to give you an example of what kind of activity we're building up. So in 4th of May, this is when we have the minute interval episodes. You can see how it's building up. It's very high fountaining. There's very little lava pooling in the cone, and the cone is relatively small, but we do still see the free surface. 9th of August, very different situation. Cone is much bigger. We have lots of lava filling the cone of the crater itself, the crater bowl. Very broad sort of fountaining, but no really high fountains. So, highest fountains subsequently in June were about 250 meters. So this is actually quite interesting or significant change. This is what happened in this small eruption. Remember, this is a low intensity, low volume, or low magnitude eruption. Eruption rate, like we said, maybe on a few cubic meters per second, volume on the order of 0.1. Yet you have all this diversity. It is kind of interesting. So it's not a more mundane or monotonous kind of event. Anyway, there are other things that do come into play there, and I'm just going to really quickly go through that. The size of the crater bowl can actually have also impact on both the periodicity and the height of the fountains. Same thing can be said about outgassed magma that resides in the vent after an episode, and then when the next one comes in, it has to interact with that outgassed magma, and that changes the whole geology of the system, and it also changes the explosive intensity. So all of these factors come into play to actually change the activity. We even had different pumices formed during the period of different magma composition. That's magma 1. Very sort of golden pumice-like grains, fairly vesicular, but very mature, partly collapsed bubble structure. The higher magma discharge event and the more enriched magma formed this really nice actinide with nice classic black surfaces, tight vesicular interior, and a fairly sort of immature bubble detectors. And now I'm just going to jump a little bit and because I like this, show you how the lava, as I can see this sea globe spreading across the bottom of the valley. Now it's completely sealed over, but it still keeps rising because you're injecting magma underneath the solid crust, as you can see from the incandescent surface breakouts on the margins. During this process, the lava increased its thickness by a factor of 5 to 10. Don't I talk? I forgot the microphone. Okay, and we won't do that again. Come on. So, to finish off the 21 eruption, at 5 square kilometers of lava, 0.1 cubic kilometers, by all measures, it is a low intensity, low magnitude event, but showed diversity beyond expectations. Also, take a note here, the thickness values of this lava. Where it's thickest, close to the vents, it's about 100 meters. The vent ramparts rise about 20 meters now above the surrounding lava, but they're 100 meters above the surface they started at. So, we should not underestimate small events. They can actually teach us a lot and show us a lot of diversity. Let's go quickly to the 22 event. So that one started on a 300 meter long fissure that sort of produced a continuous fire fountaining, sort of curtain of fire. The upslope side, which is east in this case here, small rampart started to form, but on the west side, basically lava just oozed out from the vent and filled in this pond. Now, there's a little valley here. When the eruption started, the lava was flowing into the valley, it quickly sort of ponded in there. And this is taking, so the eruption started about 7 o'clock in the morning. This is taking 3 o'clock in the afternoon. And the pond is already 9 meters deep. And I see these lavas, which are sort of breakouts from the pond. They sort of build up a support wall for the banks, which always stand up about 3 to 4 meters above the top of those lavas there. And this pond remained intact. It's almost like the lava had a memory, despite the fact that it went from 9 meters to 35 meters in a week or so. And we see the margins of the pond are always the same. The shape stayed there, which I thought was quite remarkable. Another interesting feature, and to sort of come on. Is it this too? Yes. Okay, just an introduction to what is sort of the final take on all this. Look over here. See, this is a surface breakout. It's coming over an older, already lava with already solidified top, and it's coming breaking out. But you see, it's breaking up the crust and squeezing out liquid lava. Moreover here, these two lavas, liquid lavas are blending, they're mixing. It's a dynamic mixing. I could confuse some of the geochemists if it goes further. So underneath this crust, there is basically a pool of liquid lava. And so to finish up on this, more or less, on 7th of August, we went to sample the 22 lava, which is the one that banked right back here, the active flow front, right in this area. We walked across this 21 lava to get there to the site with successful sampling, and we walked back and went home with good samples, and then we came back 3 days later As we expected, the 22 lava had advanced, which is that looking flow here. But it also had pushed up and broken up this Pahoehoe lava which was in front of it. First we thought that was this one, but quickly realized that couldn't be, because after we droned the area and we plotted up our droning data, we saw that this is the old 21 lava surface here. And this is right where the location I was showing you earlier. And the new lava is 10 meters higher. So clearly, new lava had come in there. And we found this eruption site. There was a breakout further south from the surf through an inflation cleft in the 21 lava. And this is actually liquid interior of the 21 lava. That actually broke out because the loading from the 22 lava onto the 21 lava in this region, which should point out the 21 lava was about 40 meters thick there, it basically squeezed the liquid core towards the east, inflated portion of the 21 lava, and then broke out and erupted that liquid interior in front of the advancing 22 lava. Kind of an interesting little story. And just to finish up with the 22 eruption, it's even smaller. It's an order of magnitude smaller than the 21. And to wrong tool. Finish this up. I just want to say a little bit about this. This is actually a plot where we have magnesium number, which is sort of a good indicator of magma evolution, magma fractionation, crystal fractionation, etc. And here we have this incompatible element ratio I showed you earlier. And good thing about these kind of ratios, they don't change during crystal fractionation. So they're actually a good indicator of when crystal fractionation is important. Now, the 21 erupted products, that the whole rock data is here, shows this range from the magma 1 composition to magma 2 composition. The glass data is the diamonds here. They show the same thing, slightly shifted in terms of magnesium number, but that can easily be explained by the crystal cargo that is included in the analysis of the whole rock. And it's clearly defined this mixing trend here. Lava salvages, which are the quenched out rind of lava wherever it's placed out in the lava flow field, they actually show a nice fractional crystallization trend. And Marie Noel will know a lot about this because this is part of her PhD thesis, which is degassing-induced crystallization, in situ crystallization. So they actually define this fractional crystallization trend for these. And this is interesting in the context of the 22 tephra, also lava salvages, and also the composition of the re-erupted magma. They all fall on the crystal fractionation trend of the magma 2 component of the 21 eruption. So the idea here is that the 22 magma is actually something that resided in the plumbing system of the 21 system and got pushed out in 22. And that sort of idea is also supported by the fact that this is also pushed out, even though by different mechanism. They show roughly the same degree of evolution or fractionation, if you like. Now, also another important point here is that what erupted in 21 and 22 is nothing like what has erupted previously on the Reykjanes Peninsula. These are new magmas. And another interesting thing is that most of the melt inclusions that the macrocrust carried up by these eruptions have really nothing to do with this magma here either. So they're just travelers who kind of smuggled themselves on board and snuck up to the surface. But in terms of sources, clearly this is enriched component, and it probably, if you look at trace element ratios, it sort of points towards what we think is the enriched component of the Icelandic mantle plume, and maybe that's starting to make an inroad into the Reykjanes Peninsula area. Magma 1 is possibly from a depleted part of the Icelandic mantle plume. And with that, I think I just want to stop.
So thank you very much. Fantastic talk. Questions?